At highway speed, the road can begin disappearing from beneath your tires before the puddle looks deep. Steering can turn vague, braking can fade, and the car may stop following the direction you chose. But hydroplaning does not begin at one magic speed. The real threshold is hidden inside a race your tread is trying to win. A tire does not touch the road across its whole round shape. Its load passes through a small, flattened contact patch. On dry pavement, rubber bends around tiny surface peaks, building the grip needed to steer, brake, and accelerate. In rain, that contact patch becomes a drainage problem. Water arriving at the front of the tire must escape through tread grooves and across the road texture before the rubber rolls over it. If it escapes in time, much of the contact survives. If water cannot leave quickly enough, pressure builds at the leading edge. A wedge pushes into the footprint and starts separating rubber from pavement. The loss can begin in one region before the tire is fully supported by water. Speed changes both sides of the race. The tire encounters more water each second, while every piece of tread has less time to drain it. Hydrodynamic pressure also rises sharply with speed. A road that feels ordinary at one pace may feel completely different faster. Those grooves are not decoration. They provide channels for water to leave the footprint. As tread wears, the available drainage volume shrinks. A worn tire can therefore lose useful contact sooner than a deeper tread tire in the same rain. The pavement is the other half of the system. Fine texture helps rubber generate friction. Larger texture gives water somewhere to go. Smooth, polished pavement and standing water leave the tire with a much harder drainage task. Inflation pressure changes the footprint and the pressure the tire can apply against water. Load, tire shape, tread design, water depth, and surface roughness also matter. Change one variable and the onset can move, which is why a universal car speed is misleading. You may see a neat hydroplaning formula online. Classic NASA work produced useful estimates, especially for aircraft tires, but it was never a universal speed limit for every car and puddle. Real roads combine partial contact, changing water depth, worn surfaces, and 4 different tires. The danger is not limited to the dramatic moment of a tire skiing completely on water. Even a thin film can reduce friction, and partial separation can weaken braking or directional control. The threshold behaves more like a fading connection than a single switch. The safest intervention happens before the wedge grows. Slow down for rain and standing water, leave more distance to stop, and avoid abrupt demands on steering or braking. Electronic aids can manage available grip, but they cannot create contact where water has removed it. Use the pressure specified for the vehicle, inspect tread and damage, and replace unsafe tires. These steps do not make deep water safe. They preserve the drainage and contact the vehicle was designed to use. A flooded road adds hazards beyond hydroplaning: hidden damage, uncertain depth, moving water, and a vehicle that can be displaced. If water covers the road or barriers close it, turn around. The correct experiment is the one you never perform. Rain does not simply make rubber slippery. It inserts a fluid system between tire and road, and speed decides how little time that system has to drain. The road disappears when water wins the race for the contact patch, often before the puddle looks deep enough to matter.